Happen. Some things like do grow exponentially in the real world, but that's not likely. What's far more likely is something like this. So if you think about a situation like that they always talk about, like, hey, you put 1 million bacteria in a little petri dish thing, and they start to grow exponentially. They double every 10 minutes. You with me? That's true. It might grow exponentially. That population might grow exponentially, but it's not going to go on forever. Why is it not going to go on forever? Right, you're not going to feed them all. They're not going to fit in there. They're running out of space. So exponential growth does happen. Like stuff might double. You know, the population is going to grow depending on how many there are. That's real. But it's going to do something like this. So it's going to start growing exponentially. But then what's happening here? Yeah, it's starting to like level out. They're kind of running out of space or resources or whatever it is, and it's going to kind of flatten out there. Have you guys seen a graph like this before anywhere?
Yeah, it's a sideways the cubic, right?
No. It's not a sideways cubic. What is this? What is this orange thing? It's a asymptote. Cubics don't have asymptotes. Where do you see it, Luke?
Awkward.
Yeah.
Yeah.
Yeah, I was gonna say. Yeah, that's what another class was saying too. Like, your population of whatever animal is going to grow and grow and grow, but it's going to level out here, okay? So, you with me? That horizontal asymptote is called the carrying capacity. It kind of limits the exponential growth. You with me? Right here, your growth starts slowing down graphically. What is this point? The point of inflection. So this graph's increasing the whole time, but here the rate of increasing starts slowing down. Okay, you with me? You haven't learned about the equations for logistic functions yet in a math class because they're kind of complicated. Okay, what they look like is like this.
They look like a pseudo chart.
Okay. They look like what? They look like this, okay? So this is a function that is a logistic function. If you think about what it looks like graphically, this makes some sense for a couple of reasons. First off, if you plugged in 1 billion for t, what's e to the negative something times 1 billion? Really small. Check. Super, 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 super small. What's a super, super small thing times b? Super, super, super small, basically 0. What's 1 plus 0? What's L divided by 1? What is that saying? Right. So as you plug in a giant number, what's the population getting close to? L. Okay, so that kind of makes sense. It has that horizontal asymptote built in there. It also makes sense that there's a little exponential part because there's clearly some exponential growthy part happening. L is your what?
Carrying capacity.
Carrying capacity. It's your maximum amount that it could be. It's that horizontal asymptote. Jot that down. What's K? Yeah, it's some type of something to do with the growth rate. Okay, something to do with it. We'll get back to that. What's B then? Yeah, it's something. It's some constant that has something to do with your initial condition. Okay, and we'll get back to that in a second. So why are we talking about logistic functions? What does this have to do with calculus / differential equations? Well, logistic functions are the solution to differential equations that look like this. Okay? If you look at this, what's this? What are solutions to this differential equation? Yeah, straight up normal exponential parts. The addition of this changes it from exponential to this logistic thing, okay? So if you come across an exponential function that looks, a differential equation that looks like this, the solutions to those differential equations are gonna look like this. You need to memorize these. You have to memorize these, okay? If you look here to here, a couple things I want you to notice. There's the K. There's the K. Y is the function, Y. L is our carrying capacity. What isn't present here that shows up here?
B.
So what's the B?
B.
Oh, it's constant.
Yeah, it's that plus C, it's that initial
Yeah, the
condition
initial
part.
condition.
You know what I mean? So there's a bunch of different logistic growth models, but which one works depends on.
So the B makes it a family? Is that like?
Exactly. Exactly. The B makes it a family, and why is it times instead of plus C? It's just like how we took the
Yeah.
E to the C and made it the A part. Okay. I am going to show you why you need to memorize this. Unlike the normal exponential ones, you could just separate the variables and integrate it, and it's pretty easy. This is not going to be that easy. So how could I convince you that this was the solution to this differential equation? I really have two options. I could integrate this and show I get this, or I could
Yeah.
differentiate this and show I get this. I'm going to differentiate this and show I get this. It's going to be really messy and sloppy. This is one of those things where you can follow along and write down what you want, but I want to convince you that that's the solution to that differential equation. You with me? Okay. You're already convinced?
And it's only when it's that 1 minus L over.
Yeah, it's literally, just need to look exactly like that.
Okay.
Yeah.
Could Y be negative?
These look, you can rearrange your different, we'll talk about it, okay? But yeah. All right, ready? In order to do the derivative of this, what do I need to do? What?
L's a constant.
L is a constant. So I could do quotient rule, or I could rewrite it, yeah? You guys what?
Bless you.
Okay, I could rewrite it as to the negative first. Check that you're with me so far. I haven't done any calculus. All I've done is rewrite it. Now I'm going to do the derivative. Bring the negative down, math. What's my new exponent? What do I need to remember? Okay, times, what's my derivative of this?
So Toby, could you step to the right? for-
Yeah. You're with me right here. Yeah, I did my derivative. Now if you're looking at this, this looks like absolutely nothing like this. So from here, how do I get this to look like this? I'm just going to do fancy weird algebra. Okay. First fancy weird algebra I'm going to do is I'm going to rewrite this like this. Negative L over, this is going to be squared, so I'm going to write it twice. 1 plus b e to the negative kt. 1 plus b e to the negative kt. And then up here, sorry, that negative and that negative cancel, so I'm going to have L, K, B, e to the negative k, t. I like this line, it just has no numbers in it. Just straight letters. There's just nothing. You with me? Okay. So now I'm going to say, hey, ky. What's y again? Like, y is this whole thing, right? So if you actually look, ky would be just this. I actually have this showing up. Here's ky. That works well.
Wouldn't K be on the bottom? If KY equals?
K times y, the k goes on the top, right?
Oh, yeah.
Yeah. So that green thing is right here. LK. You with me on that being the green thing? So I'm going to replace the green guy with y. And now I have this. Oh, sorry, I'm going to replace that with ky. Sorry, that's ky. With me? So then, last little thing. What's this supposed to be then?
1 over 1 minus O.
Okay.
Or 1.
Yeah. I'm gonna take this and simplify it and show that you get the blue thing. Ready? 1 minus y divided by L. Look at y. If I take y and I divide it by L, what do I get? What happens? Yeah, the L becomes a 1, so I get this. If I want to push these two things together, what do I need to do?
Multiply by 1 plus.
I need to get a common denominator. So I'm going to get 1 plus be to the negative kt minus 1 over 1 plus be to the negative kt. We're almost done. What's the top? What happens to the top? The 1's cancel. What am I left with?
B to the negative kt over 1 plus b to the negative kt.
Which is what I wanted. So this is 1 minus y over L. So then I get ky times 1 minus y over L. Cool.
Hooray.
Hooray. Summary? That's very confusing to figure out that those two things are derivative, the one's the derivative of the other is the integral of that. So how are you going to do this going forward? Yeah, you're going to memorize it. You just gotta kind of. You're not going to do that derivation, okay? So you need to remember that if you have a differential equation that looks like this, that logistic function model. And this is kind of the last thing with differential equations that we're going to do, and it is confusing, okay? Because it gets a little tricky. You want to do an example?
No.
Yeah. All right, we'll do one. All right, we'll do an example. Okay. Hey. They put 10 grizzly parks, or 10 grizzly parks. Oh no, bad start. This is bad. They put 10 grizzly bears in a national park 10 years ago. Okay? So that was at the beginning, they put in 10 at time 0. You with me? Yeah, I got confused about that. Alright, so now it's 10 years later, they've been growing. Now there's 23 bears. So now we're at 10 years later, there's 23 bears. Okay? They're saying, hey, it's bears in a national park. They can grow, but the park's only so big, so they might start growing exponentially, but it's gonna flatten out. And they know somehow that the maximum amount of bears they can have is 100 bears. They're saying, hey, find a logistic growth model that models this and tell me when these populations will be hit. Okay? So let's just jot down our logistic growth model. Okay, we can look back at the last page if you want, which I do want to. And keep in mind it's y as a function of t. So y is going to stay a variable, t is going to stay a variable. What do I need to, anybody know one of them right away? Yeah, read it.
B is 10 because that's the initial condition.
It doesn't work exactly like that. It's not like b is the initial amount. B has, like, some value of b gives us the initial amount.
Oh, yeah.
You know, it's not exactly like that.
All right, well, then we can do 100 for L.
Cool, I like that. That's definitely true. What do we need to figure out?
B.
And,
Okay.
okay, we got to figure out these two different things, okay? Let's find, let's figure out which one's easier to find first is really what we're going to do. And what we're going to do is we're going to plug in the initial condition. So the fact that at time 0, y is 10. At the initially, the population was 10. Okay, so I'm going to plug in 10 for y. I'm going to plug in 0 for t. 0 for t. Well, that's just going to go away. That's just going to be 0. Oh, sweet. So I'm going to get 1 plus b on the bottom. This is nice. What's b?
Oh,
9. Yeah, 1 plus 9 is 10. 10 divided by, or 100 divided by 10 is 10. You can solve it out, but you're cool. I just figured out b. I just figured out Yeah, the b what b is.
Yes.
Cool. I figured out b. So I almost have an equation I can use. What am I still missing?
Okay.
Okay. And how am I going to figure out k?
Plug in 10 for T, 23 for Y.
Thank you. Why did I not? Well, actually, yeah, I'm gonna ask that now. Why did I plug in this point first instead of this point? Yeah, like plugging in a 0 for one variable is usually a better idea because it might eliminate something like happened there. Okay. Otherwise, I could have a system situation. 2 variables, 2 equations, which we will hit. But this way I avoided that. 10 for, or 23 for Y, 10 for T. All right, now we gotta do some math. Math.
We haven't done
No. I'm gonna do this kind of math.
that. Oh, crunch.
Okay, divide that all by 9. Whatever that is. Someone want to grab a calculator? What?
77,207.
207.
Okay, cool. And I'm almost done, right? I'm gonna ln both sides. Sorry, my brain's not working. Divide by -10. And we get k equals, let's get the decimal. Oh, no, it doesn't matter. You don't. Can someone toss that in? 0.09889. Cool. And I did it. I found k. And so now I can go back up and I can actually write my function. I think I got it somewhere here. See if we got it right. Is that what you got?
It is original.
Wow. Can't believe you did that right. Incredible. Okay, now I wrote my function. Again, I haven't done any calculus, but we're just doing a problem with a logistic function. Now I have my logistic function. What were they asking me? Okay, so say that again.
When O's reach 50.
Okay, so they're asking me for the t when the output is 25, 50, or 75?
Or 50, 75.
Okay, so I'm gonna say 50 equals this. Everybody look right here. You guys don't like your calculators for some reason. I don't know why.
What do you mean?
There's like a perpetual problem with you guys trying to do, like, how could you solve this?
Subtract.
You could do a bunch of algebra stuff, or you could do what?
Graph it.
Graph it and figure out when this hits 50. So let's type in the logistic into your graphing calculator, and then just type y equals 50, y equals 75, and do second calculate intersect and figure out the time when that happens. Okay.
It's quite long.
These problems, because they're so messy, are going to be likely would be a calculator one if they asked you to do something like this because it's messy. Okay. So again, you're going to go to your y, type y equals 50, type y equals your logistic growth model. Figure out where they intersect. Okay. And that's all we're doing graphically here.
Yeah, how do you turn it off?
Everyone has their
slope field.
Yeah.
Oh.
You have to clear the function and then I think you have to go to format and turn your axes back on.
Oh, is that how you do it? So you want to say it again, Demeter?
Well, let me double check that's right.
Oh, maybe if you just hit Zoom 6.
Zoom 6 might do it, or
Yep, Zoom 6 will make it go away. But then you probably want to adjust your window so that it's only positive X values and the Y values go up. Cool.
Wait, Mr. Perry,
Yeah.
can I ask you a question?
Mhm.
How do you figure out when the Y value equals
Okay.
You put y equals 50.
Yeah, how?
Oh, you literally put y equals 50 as a second equation. And then I find where they intersect.
You're doing that.
Yeah, that's
I like
always-
doing the minus.
No, I know. There's a lot of, that's like a persistent problem. Like, no, you type both sides in as different y equals and you figure out what they crisscross. Cool. I was going to say one other thing. This is kind of weird. I don't really know. Last thing. Hey, this is a weird answer. Why is this weird?
Because it never reaches it.
Right, isn't that a horizontal asymptote? So why is this a thing? I think it's a rounding situation, right? Like, the population's gonna be 99.5 or more then. So that's when you might have 100. That's the carrying capacity, so you're never gonna actually hit it. It's a horizontal asymptote. I think that's a rounding. All right, you guys are good to go.
Where's the tiny plus sign?
Oh yeah.